In the world of technical design, standard professional practice often dictates keeping complex visual elements cleanly separated from their explanatory text. You see this when a textbook places a dense legend at the very bottom of a complex diagram, or when a software manual sits physically separate from the application screen you are trying to learn. While this separation creates a visually pleasing, minimalistic layout, it ignores the strict biological constraints of the human brain. Human cognition relies on working memory, a processing center with severe, hardwired limits. It cannot handle unnecessary logistical tasks without degrading performance. When learners are required to divide their focus between multiple, separated information sources that are unintelligible in isolation, they experience what is known as the split attention effect. The tension between these two worlds suggests that a layout optimized for the eye might actually be an obstacle for the mind. Cognitive load theory is grounded in the narrow limits of change principle. This dictates our working memory has a rigid capacity for novel, interacting elements. Effective learning uses this capacity to build organized mental frameworks, or schemas. In instructional design, the mental effort directed toward this actual learning is classified as germane cognitive load. Extraneous cognitive load, conversely, is the mental effort wasted on the format and presentation of the material itself. Forcing a learner to search a page for spatial reference, such as matching a label and a legend to a specific line on a graph, creates extraneous load. This diverts finite processing power away from schema formation. Any physical distance between mutually dependent pieces of data operates as a massive tax on human cognition. In 1988, researchers Termesi and Sweller set out to study the worked example effect in mathematics. Prior studies had established that providing students with step-by-step worked examples was a highly effective method to reduce cognitive load in algebra. When Termesi and Sweller applied this exact same method to geometry, the worked examples failed to improve learning at all. This diagram shows the specific format used. A geometric triangle is presented with solution steps separated below. To trace the solution, learners read a step, scan up to find the angle, then look back down. This constant scanning maxes out the brain's processing limits. To understand the geometry problem, the diagram and the text must be mentally integrated. The separated layout forces the brain to execute that integration while simultaneously managing the visual search. Neither the isolated shape nor the isolated text block contains enough context to be intelligible. They are mutually dependent. The layout imposed an extraneous load so heavy that it effectively blocked the student's ability to process the geometry itself. The failure of the worked example method in geometry demonstrated that the spatial mapping of attention is a primary bottleneck in complex learning. Termesi and Sweller resolved this by redesigning the geometry problem. They physically embedded the text directly onto the diagram at the exact locations of the relevant angles. Positioning explanations at the exact spatial coordinates of their visual reference eliminates the need for visual search. Students using the integrated layout required less time to study the material and outperformed the split source group on both similar and transfer problems. The physical design layout now performs the integration on behalf of the user, acting as a cognitive prosthetic. This principle holds across disciplines. A subsequent study by Ward and Sweller examined students learning kinematics. They found that integrating complex mathematical equations directly into the text of physics problem statements removes the need to constantly cross-reference separated values. The effect also dictates outcomes in language acquisition. Look at this comparison. Placing phonetic translations, known as pinyin, horizontally away from Chinese characters hinders learning, compared to a physically integrated vertical stack. Regardless of the discipline, physically unifying dependent sources allows working memory resources to be concentrated exclusively on schema acquisition. Working memory treats temporal distance exactly like physical distance. This timeline visualizes a study by Mayer and Anderson on temporal split attention. When teaching students how mechanical systems operate, presenting an audio narrative before a visual animation, rather than simultaneously, caused test scores to drop. Narrating an animation before or after it plays forces the brain to buffer the audio and mentally superimpose it. This delay spikes extraneous load. To optimize learning, audio narrations must be perfectly synchronized with their corresponding visual actions. A common professional objection to spatial integration is that embedding all explanatory text onto a single diagram causes severe visual overcrowding. Research by Beitrancourt and Erhel offers a modern user experience solution to this clutter. They tested a pop-up procedure, where text is embedded at the relevant position, but remains hidden until the user clicks the specific node. Synchronizing time and utilizing user-triggered localized pop-ups eliminate visual search without sacrificing layout clarity. Physical integration is bound by a strict condition known as element interactivity. Low-element interactivity tasks are simple, sequential operations, like basic vocabulary translation, that require very little working memory to process. The split attention effect does not apply to these simple tasks. The cognitive load is already so low that the brain can easily handle the spatial separation. High-element interactivity tasks involve complex, intertwined variables, like calculus, CAD software, or electrical circuits. Here, integration becomes mandatory. The ultimate boundary condition for integration is that the multiple sources of information must be unintelligible in isolation. This diagram shows what happens if the visual is fully self-explanatory on its own, but a designer forces integrated explanatory text onto it anyway. It creates a cognitive clash. Forcing learners to process integrated text when the visual alone is sufficient triggers the redundancy effect. This actively harms learning just as much as splitting essential information. Standard, separated instructional layouts create a false economy. They look clean, but they outsource the heaviest cognitive lifting to the user. Human working memory is a biological bottleneck. It cannot be overcome by simply asking the user to try harder. Designers must treat interface layouts and instructional materials as cognitive prosthetics, explicitly engineered to bypass these hard biological limits. Whether through spatial embedding, through temporal synchronization, or interactive pop-ups, the design goal is the total eradication of visual search. To optimize complex learning, designers must integrate disparate sources to build the schema on the screen, so the user can build it in their mind.